Welcome to Pomodoro Joe for Friday, May 19th, 2023. Today we're looking at LeetCode problem 785, is graph bipartite? This is a medium problem. There's an undirected graph with n nodes, where each node is numbered between 0 and n minus 1. You are given a 2D array, graph, where graph index u is an array of nodes that node u is adjacent to. More formally, for each v in graph index u, there is an undirected edge between node u and node v. The graph has the following properties. There are no self-edges, so graph index u does not contain u. There are no parallel edges, so graph index u does not contain duplicate values. If v is in graph index u, then u is in graph index v. The graph is undirected. The graph may not be connected, meaning there may be two nodes, u and v, such that there is no path between them. A graph is bipartite if the nodes can be partitioned into two independent sets, A and B, such that every edge in the graph connects a node in set A to a node in set B. Return true if and only if it is bipartite. All right, so I'm going to paraphrase this just a little bit. We're given a graph. This is a 2D array, where the index into the first array will just be the node number, so 1, 2, 3, 4, 5, etc. The value at that index will be another array, and that array contains all of the nodes that this node is connected to. So if you look at index 5, that'll be an array of all the nodes that node 5 is connected to. We're also told that this graph is undirected, so that if you look at node 5 and you find all of the nodes that it's connected to, if you look at any one of those nodes, you'll find node 5 in their connected node list. So for example, if node 5 contains node 8 in its list, then node 8 will contain node 5 in its list. So we're given this graph, we have all of the edges. Now we need to find out if there's a way to partition all of these nodes into two different sets, such that if you look at any node in set A, all of its edges will connect to nodes in set B. And if you look at any node in set B, all of its edges will connect to nodes in set A. So there will be no edges that connect a node in set A to another node in set A, or a node in set B to another node in set B. That's all this is saying. All right, then we have a bunch of constraints. But I think we get the idea. So with that, we will put 25 minutes on our Pomodoro timer, and we will get started. We'll start out with some result, and I'm going to assume that it's true until we find a counter-positive example. So basically, I'm just going to assume that this is true until we find a node that connects to another node in its own set, and then we can return false. So our result will start as true. Okay, so how do we do this? Now, we don't really know which set any node belongs to at the beginning. So at this point, we can just grab a node, say grab node 0, and we'll just assign it a set. So at the beginning, we'll have to assign a set because we don't actually have sets yet. So we'll create a couple of sets, and then we'll assign, say, node 0 to set A. Then look at all of the nodes that node 0 is connected to, and just assign them to set B. So first, let's just create a couple of sets. So we'll just have set A, and we'll just call it a set, and we'll have a set B. In the beginning, none of our nodes are in a set, so we can just assign a node to a set. So we can say for every node in our range, well, we actually don't know how many nodes we have, so let's create our n here. N will tell us how many nodes we have, and that'll just be the length of the graph. So for every node, we'll just check to see which set it's in, and then we can put all of its connected nodes in the opposite set. But at the beginning, we don't actually know which set a node is in. So we'll just have to sort of assign it to a set. So we could check, we could say if node is in set A, well then the opposite set will be set B. So let's have like a current set and an opposite set. We don't know what they are yet. Okay, so if node is in set A, then the current set will be set A, and the opposite set will be set B. If current node is set B, then we have the opposite of this. So I'm just going to copy and paste here. We're going to go through and clean this up later, so don't worry too much about this. All right, so if the current node is already in set A, well then we can set our current set and our opposite set. If the current node is in set B, then we set our current set to set B and our opposite set to set A. All right. If we don't have a set though, so in the very beginning, node 0, it's not going to have any set. So we'll just assign it a set. We'll just say, we'll put it in set A. So that means that we can actually do something a little bit simpler here. We can just initialize these to set A and B, and then swap them if we need to. All right, so we'll just assume it's already in set A. So if it doesn't have a set yet assigned, we'll just throw it into set A. If it has set A already assigned, well then this is going to take care of that. Otherwise, if it's got set B assigned, then we'll switch these to be current set is set B and the opposite set is set A. Okay, so now we have our set for our current node and we have the opposite set from this current node. So at this point, we want to go through all of its connected nodes and put them in the opposite set. Now there might be a problem here. What if we've already assigned a set to that other node? If we've already assigned a set to one of these connected nodes, then we can verify that it's in the correct set, the set that we expect it to be in. Or if it's not, then we can return false. We know that this is not going to work. This node is connected to another node in the same set, and that would be a problem. All right, so for every connected node in the graph for this node, well, let's see, we'll check to see if it's in the same set. So if this connected node is already in the same set, well then we'll return false because we can't connect to a node that's in the same set. Otherwise, we'll just assign this node to be in the opposite set. Okay, so we'll be checking to see if this connected node is in our same set. If it is, then we return false. We can't do this. If it's not, then we'll just make sure that it's in the opposite set. It might already be in there, but we'll just throw it in there again in case. Nice thing with sets is they are unique values, so we can throw it in there and not worry about it. Okay, so now we have our basic setup here. We're going to go through every node, look for that node in a set. If we don't know what set it's in, we're just going to put it in a set, and then we're going to put all of its connected nodes in the opposite set. If we find a node in the connected nodes that's already in the same set, well then we have to return false. Now there is a problem with that approach. If we get to a node that hasn't been assigned a set yet, and we throw it into set A, it's possible that that node was meant to be in set B, and all of its connected nodes should be in set A. And if we put it in set A, then we've broken things. So how do we get around this limitation? So the trick here is to actually follow these connected nodes down the line as far as you can. So by grabbing a node, putting it into a set, then putting all of its connected nodes into the opposite set, if we follow those connected nodes, check all of their connected nodes, and put their connected nodes in their opposite set, and we keep following that trail down, then we exhaust our graph, and we know that we've put everything in the right set. Then if we come across another node that's not connected, or that doesn't have a set assigned to it yet, then we know it's not actually connected to this same graph. It's got its own graph. And we can assign it to any set we want because it will be a complete unique set of nodes and connections. So that's kind of the trick here. So this is very similar to a depth-first search. So we can do something with a stack. That's what I usually go for, is just have a stack. So we'll start off with some stack, and we'll have to put the node in the stack to kick things off. All right, and then while we have a stack, then we do all of this stuff here. Okay, so we're going to go through every node. We're going to put that node into a stack. Then while we have some node in the stack, then we'll actually have to pop this node off the stack. So at this point, I'll call this node. I'm going to call this one I for the index of the node. And the node itself, we're just going to pop off the stack. I'm going to pop it index 0, although I don't think it really matters. So we're going to grab this node off the stack. Its current set will be set A. Its opposite set will be set B, unless this node is already in set B, in which case we'll flip that around. Next, we'll go through the connected nodes. If the connected nodes are already in the current set, then we return false. This is broken, or this has a node connection that goes from the same set to the same set. Otherwise, we're going to put this node into the opposite set, but if the node doesn't already have a set, we want to recurse on this node. So we do want to follow this node. We don't want to end up going in infinite loops. So we only do this if we haven't assigned that node to a set yet, meaning we haven't visited this node. So if this connected node is not already in the opposite set, we'll add it to the opposite set and we'll push it onto our stack. So we still need to process this node. All right, now we're getting somewhere. So we're gonna push this node onto our stack, and then we'll come back up here and we'll continue down the line until we reach the end and we have no more nodes in our stack. If we ever end up with a node that connects to another node in the same group, well, then we'll return false. Otherwise, we'll exhaust this complete graph and then move on to the next graph by moving on to the next node in our range here. At the very end, we will just return our result, which we've never done anything with. So we might actually get rid of this result and just return true at the very end. Okay, so let's go through this really quickly before we try running it. So we're going to grab the length of our graph, so that's going to tell us how many nodes we have. Then for every index of the node, or node number, we'll go through, we'll create a stack starting with that node while we still have the stack. So while there's still nodes in our stack, we'll grab a node off the stack, we'll set its current set to set A and its opposite set to set B, but this is just our initial value. We might need to flip that around if we've already set this set for this node. So we'll check to see if this node's already in set B. If it is, then we'll flip that around. Then we'll look at every connected node for this node. If we've already put that connected node into this same set, well, then we have to break out and we return false. If we haven't put this connected node into this set, then we'll check to see if it's already in the opposite set. If it's not already in the opposite set, then we'll add it to the opposite set and we'll put it on our stack because we need to follow its connected nodes down the line. If we've already put it into a set, then we don't need to put it on the stack because we've already processed this node. If we make it to the very end, then we can return true because we didn't find any of these sort of nodes that are connected to other nodes in the same set. And we do have to do this for every node in our range. Now, let's see, there might be ways to shorten this up a little bit. For example, when we put this node in our group here, or in our stack, if it's already in a set, we probably don't need to even put it in the stack because we've already processed this node. So we might want to do that. So if we've already processed this node, let's just move on. We don't need to process it again. Okay, let's try this. Seems to work. Let's see how we do. And we pass. We do okay. We beat 43% for runtime and 31% for memory, so that's not too bad. Now there's a lot of different things you can do with this one to speed it up. I'll just point a couple things out. I don't know if we'll actually try them, but you can check them out. So number one, these sets. We don't actually have to use sets. We could just create a list or an array that tells us which set these nodes are in. So for example, we could have a node to set mapping. And that can just be an array. And actually, I'll put it after my length calculation here. So we can just set it to something like 0 times n. So we initialize these all, and we can do something simple, like we can say our set, let's say unknown is going to be 0. We don't know which set it's in. We'll say set A will be equal to 1, and set B, let's set that equal to -1. That way it's easy to just get the opposite. So if you just grab set A, which is 1, and negate it, get -1, you're in set B. So that makes it easier. You don't actually have to do this It's not that complicated, but you don't have to do this logic here. You could just immediately set your opposite set by getting the opposite of your current set. So you could use this mapping instead of keeping these sets. That might speed things up a little bit. So that's one thing you can do. What else can you do? And you could try popping 1 instead of popping 0. You could try, well actually, let's try something really quick here. So before we go down this path, let's try changing our stack here from a regular list into a deck. Now a deck is a data structure that's really good at pushing and popping. It's a lot faster than a regular list. So let's try using a deck. It's double-ended queue. That's where the name comes from. So we'll just create a deck. And instead of doing a pop 0, we do a pop left. And the append stays the same, so we don't need to do anything there. Let's see if this still works. And then let's see if this gives us any gains in our runtime. It may or may not. It should be faster. All right, so that is faster. So we are now at 69% for runtime. That's up from 43%. So yeah, that's significant. A little bit worse on memory, but much better runtime here. All right, so let's just do a quick review. The key to this one is really understanding that once you assign a node to a set, you have to follow the node's entire graph until you've exhausted it, assigning those nodes to opposite sets. So you assign one node to a set, you have to follow its connections to all of its connected nodes, assign those nodes to the opposite set, then you need to put those nodes onto a stack so that you can process those nodes and their connected nodes, pushing their connected nodes into opposite sets, and keep following that until you've exhausted that graph. All right, well, 69% is the best I'm going to get today, and I encourage you to try this one. There are other things you can do to speed this up for sure. So that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.